Hi, welcome to video 3. In this video, we're going to do two types of analysis. First, we're going to do optimal choice analysis, and then once we've completed optimal choice analysis, we'll work on deriving demand functions. For this video, we're going to work with a Cobb-Douglas utility function, and specifically we'll work with u equal to x times y cubed. And so in the first part of the video, we're going to do optimal choice analysis. What we're going to basically do here is think about solving a problem where we're looking to maximize the consumer's utility subject to staying on a budget constraint. So we want to maximize this Cobb-Douglas utility function subject to staying on the constraint that we've written out. Before we get started, though, we need to know what solution techniques we might have at our disposal. And in particular, a question that we need to think carefully about is whether or not we can use Lagrange's method. If we're going to use Lagrange's method, we need for two things to be true. We need downward sloping indifference curves, and we also need for the marginal rate of substitution to be diminishing. Taken together, these basically mean that we have what economists will sometimes refer to as quote-unquote well-behaved preferences. So anytime that you find yourself confronting a utility function that's quote-unquote well-behaved, in other words, it's got downward sloping indifference curves and those indifference curves have a diminishing marginal rate of substitution, if those two things are true, then you can use Lagrange's method. And that's good news for us because if we can use Lagrange's method, we know exactly what our solution procedure is going to end up looking like. As we skip ahead to the next slide, we'll want to think about what exactly is going on with the marginal rate of substitution. Now, you may know already what Cobb-Douglas indifference curves look like, and generally speaking, Cobb-Douglas indifference curves are going to have a nice smooth shape. So they'll look something like this. Depending on the exponents, they'll be tilted one way or another, but ultimately they'll have a nice smooth shape. They don't touch the axes, and they have a diminishing marginal rate of substitution. We can see pretty easily from the picture that they are definitely downward sloping, so we don't need to worry too much about checking for that condition. But for the second condition, diminishing marginal rate of substitution, we can see that from the picture too, but let's just double check and work on that mathematically. So the marginal rate of substitution is something we find by taking the marginal utility for good x and dividing that by the marginal utility for good y. We find the marginal utility for good x by taking the partial derivative of the utility function with respect to x. So in this case, when I take the partial of the utility function with respect to x, I get back y cubed. And when I take the partial derivative with respect to y, that'll give me the marginal utility for good y. And that derivative, more specifically, is going to be 3x y squared. Now that marginal rate of substitution may look a little bit ugly, but if you do a quick bit of simplification, what you'll notice is you're actually left with something that's pretty straightforward, namely y divided by 3x. Now, with the graph that I've created, again, it's just a general graph for Cobb-Douglas preferences, we can just talk ourselves through what's happening to the marginal rate of substitution at three different points to confirm that this is, in fact, a diminishing marginal rate of substitution. So at bundle A, you'll notice we've got a lot of y and, relatively speaking, a small amount of good x. So that means our numerator here is going to be large, and then 3 times x, when x is a small number, is still going to be relatively small. So that marginal rate of substitution, which is the absolute value of the slope of that indifference curve, that MRS is pretty high. In other words, the slope toothpick associated with that curve is pretty steep. If we go down to bundle B, well, now we've got moderate amounts of y and x, and so we're going to see the MRS fraction start to shrink. And by the time we get down to bundle C, well, now we don't have very much y at all, so our numerator here is going to be quite small. We've got a lot of x, so we'll have 3 times a fairly substantial quantity of x. So we've got a small numerator, a big denominator, and that means, again, our slope toothpick reflecting that MRS is going to be fairly flat. So we know for sure that we have the 2 conditions met, downward sloping and diminishing marginal rate of substitution. That tells us we can use Lagrange's method, and so on the next slide, we'll see about setting up that problem. On this slide, we're going to do the optimal choice analysis that we had talked about on the previous slide. So once again, the problem that we're looking to solve is we're looking to maximize the consumer's utility subject to a budget constraint. What distinguishes optimal choice analysis, what we're trying to do on this slide, from what we'll be doing a bit later, namely deriving demand functions, is that in optimal choice analysis, we're actually going to make use of price and income data that we might be given in the problem. So I'm going to assume that the price of good X is $2, price of good Y is $3, and that our consumer has $400 to spend on these 2 goods. That allows me to write down the following Lagrangian. So I have x times y cubed, so that's my objective function, minus lambda, the Lagrangian multiplier, times our constraint. And what I'm going to write in here is 2x plus 3y minus 400. What you'll notice is I've basically written down the following. If I plug in the price and income information into the budget constraint, and then if I rearrange terms so that I move everything to the left-hand side and set that equal to 0, well, all I've done is I've taken that bit of information that's on the left-hand side of the equal sign and I've plugged that in to the parentheses here. So my Lagrangian has the objective function minus lambda times the constraint. In order to solve this optimal choice problem, I need to ultimately set up a series of first-order conditions. So what we're going to do here is take the partial derivative of the Lagrangian with respect to good x, with respect to good y, and then finally with respect to the Lagrangian multiplier. So let's go ahead and start with the partial with respect to good x. We'll get y cubed minus 2 times lambda, and I'm going to set that equal to 0. And then take the partial with respect to y. I'll get 3xy squared minus 3 lambda equal to 0. And when I take the partial with respect to lambda, I'm going to get back my constraint. And again, set that first order condition equal to 0. I'm going to take that third first order condition and simply rearrange the terms to give me my constraint back. And I'm going to put a box around that equation and label it as equation 2. I'm going to need that in just a few seconds, so we'll come back and work with that. But let's turn our attention to the first order condition. You'll notice I can rearrange this in the following way. Y cubed over 2 equal to lambda. And then the second first order condition I can also rearrange. I'll have 3xy squared all over 3 equal to lambda. Well, I've got 2 things equal to one another, and equal to the same thing, so they must be equal to one another. So I can rearrange this again. I'll have y cubed over 2 equal to 3xy squared over 3. I'm going to do a little bit of additional algebra work on this, and when I do that, notice we get some cancellation here, and I can get y cubed over xy squared equal to 2 over 1. So rewriting that on a new slide, we have y over x equal to 2 over 1, or y is equal to 2x. I'm going to label that equation 1, and for my next and final step, I'm simply going to plug equation 1 into equation 2. Now recall equation 2, that was just my budget constraint. 2x plus 3y equal to 400. So that's equation 2. I'm going to plug equation 1 into equation 2. That's going to give me 2x plus 3 times 2x equal to 400. Gather up some terms here in our next step. So 8x is equal to 400. So x has got to be equal to 50. And y is going to have to be equal to 100 since y is equal to 2 times x. And again, following convention, I'll just put the asterisk next to those values indicating that those are in fact optimal values. On our final slides, we're going to turn our attention to deriving demand functions. And the good news is all of the tools that you just developed doing optimal choice analysis will once again apply as we're deriving demand functions. Literally the only difference between what we've just done in the optimal choice analysis and what we're about to do in deriving demand functions, we're going to leave the notation and the constraint in the most general form possible. So we're not going to plug in any values for the price of good X or the price of good Y or income. We're simply going to solve this problem using this very generic notation. So let me go ahead and clean this up before we start. Once again, we're going to set up a series of first order conditions. We'll take the partial of Lagrangian with respect to x, with respect to y, and then finally with respect to the Lagrangian multiplier. So you've already seen a fair bit of this. Let me go ahead and write down the partial derivative with respect to x. We get y cubed minus px times lambda. So a little bit different than the optimal choice analysis simply because we're leaving that price of x as px and not plugging in a number. We'll take the partial of the Lagrangian with respect to y, get 3x y squared minus py times lambda, and again set that equal to 0. And then finally we'll get our constraint back. Px times x plus py times y minus I, and that is all equal to 0. Now again, that final first order condition is just going to give us what I'm going to label as equation 2. So I'll go ahead and put a box around that and label it as equation 2. And up here with the first two first order conditions, again, something very similar. I can say that y cubed over the price of good x is equal to lambda, and 3x y squared over py is equal to lambda. And so those two things, since they're each equal respectively to lambda, can be set equal to one another. So y cubed over p of x is equal to 3xy squared over py. I want to do a little bit of work on this to simplify it into a slightly more user-friendly format, and what you'll notice is that I get y over 3x equal to px over py. I'm going to put a box around that expression. That's going to be my equation 1. I've copied over equation 1 and equation 2 from the previous slide so that we have those to work with. You'll notice it's going to be helpful for us if we think about rearranging equation 1. What I'm going to do is move that 3x term back over to the right-hand side. And what I'll have then is px over py times 3x on the right-hand side. That's going to be helpful for me because what I want to do is, once again, plug 1 into 2, as I've indicated up here. And in order to do that, I'll use the rewritten version of equation 1, so that I'm going to have px times x plus py. And now I'll use that rewritten version of equation 1. So that I'll have px over py times 3x plugged in 4y, and then that's all equal to I. Now again, we've got to be a little bit careful here as we do some simplification. You'll notice that the py terms are going to cancel. So I've got px times x plus px times 3x. Well, what that really does is it gives me 4 times px times x, and that's going to be equal to I. And that means ultimately that x is going to be equal to 1/4 times I over px. And there we have it. That's our demand function for good x. If I wanted the demand function for good y, I could simply go back to equation 1 up here, rearrange that so that I've solved explicitly for x, that it would make it easy to plug into my budget constraint, in other words, equation 2. Just doing that, doing a little bit of algebra, what I'd ultimately end up with is that y would be equal to 3/4 times I over py. So we have demand for good x, and now finally demand for good y. And those are our Cobb-Douglas demand functions when our utility function is x times y cubed.